Hello students, welcome to Science Studies YouTube channel. If you not subscribe this channel, please be subscribed. In this video, we are going to learn two important topics. The first one is critical angle and the second one is total internal reflection. What is critical angle? What is critical angle? To understand critical angle, just imagine there is two mediums. This medium is a denser medium. This medium is a rarer medium. So the denser medium refractive index is N2 and the rarer medium refractive index is N1. Then it acts as a interface. This perpendicular line is a normal line. Now pass the light ray through the denser medium to rarer medium. From where to where? Denser medium to rarer medium. We know already when the light passes from the denser medium to rarer medium, it bends or deviates away from the normal. So here I am passing ray 1, means incident ray 1 with a certain angle. This is a incident ray with a certain angle. So the angle of incident of this ray is I1. Then it deviates away from the normal. So this is refractive ray. This angle of refraction is R1. Look at here, it obeys to the Snell's law. According to Snell's law, N1 sin I equal to N2 sin R. So at here, N2 sin I1 equal to N1 sin R. Because at here we are passing the light from the denser medium to rarer medium. So denser medium, in the denser medium the incident ray is I1. So in the denser medium the refractive ray is N2. That's why we written it N2 at here. So N2 sin I equal to refractive index N1. So N1 sin R, refraction takes place in the rarer medium. So rarer medium refractive is N1. So N1 sin R1. So it obeys to the Snell's law. Okay. Next, this ray, incident ray 1. Now I am passing another incident ray. I will consider the another incident ray as a angle is I2. What is that? I2. Then this incident ray refracts away from the normal. This angle is called R2. This ray also obeys to the Snell's law. Look at here, N2 sin I2 and N1 sin R2. Now I am passing another incident ray through the second angle. So another ray, this pink color ray is another ray. So actually it is I3. Says or no? This is I1, this is I2, then this is I3. When I pass this light through the second angle, this ray not goes to the rarer medium and also it grazes through the normal line. Actually it is a normal line. The ray when it passes from the denser medium to rarer medium, that should be passed from the denser medium to rarer medium, it deviates. But at a certain angle, the incident ray goes from the denser medium to rarer medium. But when it strikes the interface at the center point, it not goes to rarer medium. Without entering into the rarer medium, it grazes through the interface. So this angle actually 90 degree. So this angle of refraction is angle of refraction is 90 degree. So this I3 actually called critical angle. So angle of incident equal to, what is that, I3. So actually I3 equal to critical angle. So I3 equal to critical angle. Now I am substituting these values in the Snell's law. We know already what is the Snell's law? N1 sin I equal to N2 sin R. This is the Snell's law. Yes or no? So if I am taking this N1, I will bring N2 to here, and sin R by sin I. We know already N1 by N2 equal to sin R means how much? Angle of refraction R is 90 degree. So 90 degree by sin I means how much? Critical angle I3 equal to critical angle incident equal to critical angle C. So sin C. This is sin 90. Sin 90 value. What is the sin 90 value? 1. So 1 by sin C. By sin C. Next, from this N1 by N2 equal to 1 by sin C. 1 by sin C. So I want to find out the sin C value. So I need sin C. Sin C equal to 1 by N1 by N2. We know well N1 by N2 equal to N12. Refractive index of the first medium respective to the second medium. N12. So we can write sin C equal to 1 by N12. This is the formula of critical angle. What is the critical angle? So critical angle can be defined as critical angle can be defined as when the angle of refraction is 90 degree, then the angle of incident in denser medium is called what is that? Critical angle denoted with C. Are clear? So critical angle means critical angle can be defined as when the angle of refraction is 90 degree. Look at here, the angle of refraction is 90 degree. Then the angle of incident in the denser medium. So in which incident ray the angle of refraction is 90? Not at I1, not at I2, not at I2, but at I3. So I3 is a critical angle denoted with C. So then the angle of incident in the denser medium is called critical angle denoted by C. This is about critical angle. Now we are going to learn about the total internal reflection and their applications. The next concept is total internal reflection. So as we discussed in the before, this is the normal line and it is interface. This is rarer medium and it is a denser medium. So when we pass the light at a certain degree, if the angle of refraction is 90 degree, then this angle is called critical angle. It is also obeyed to the Snell's law. How? Sin C equal to sin 90 degree, like this Snell's law. Now, a question at here. It is the critical angle and the angle of refraction is 90 degree. If we increase more than the critical angle, what is the behavior of the light? So this is the critical angle. For example, 40 degree, it is the 40 degree. Just imagine, take a example value, it is the 40 degree. So this 40 degree is the angle of, this 40 degree is the critical angle. Then what will happen if we increase more than 40? Means 42, 43, 44. Look at here, when we increase the incident ray angle more than the critical angle, then the light bounces back without entering into the rarer medium. Means when the light ray travels from the denser medium to rarer medium, it reflects back. It reflects back into the same density medium is called total internal reflection. You have to remind this point in your brain. The total internal reflection phenomena takes place when the angle of incident is more than the critical angle. More than the critical angle. So as I said an example, it is the critical angle. If I increase the incident ray more than the critical angle, the incident ray travels through the density medium, but it not enters into the rarer medium. Without entering into the rarer medium, it again reflects into the same density medium. This phenomenon is called total internal reflection. So what is the definition of the total internal reflection? It is very easy. What is the definition? Look at here. When the light passes from denser to rarer medium, it is the denser medium, it is the rarer medium. When the light travels from the denser medium to rarer medium, with angle of incident more than the critical angle. So with angle of incident more, it is the critical angle more than the critical angle, then the light rays reflect to same denser medium. So this light ray reflects, come back to same denser medium without entering into the rarer medium. Without, actually it should be goes like this, goes to the rarer medium, but without going to the rarer medium, that come back. This phenomena is called total internal reflection. Are you clear? Total internal reflection. Look at here. This total internal reflection also follows law of reflection. What is the law of reflection? There are two laws of reflection. What is the two laws of reflection? The first law, incident ray and reflected ray and normal line lays at a point in the same plane. So yes or no? That is the first law. It obeys to the first law of the reflection. What is the second law of reflection? Angle of incident equal to angle of reflection. Angle of incident equal to angle of reflection. It is the second law of reflection. So it is also obeyed to the second law of reflection. This is about total internal reflection. Now we are going to discuss about what are the applications of the total internal reflection, in which way the total internal reflection and refraction of the light useful in our day-to-day life. Let's go to know about them. Okay, until now we already discussed about what is the meaning of critical angle and how that critical angle forms, and also about the total internal reflection. Now we are going to learn about what are the applications of the total internal reflection. Total internal reflection plays an important role in the glittering or brilliance of the diamond. We know diamonds shines very well. It glitters always. There is a strong reason behind that. That reason nothing but due to the total internal reflection, diamonds glitters. Actually, diamond critical angle is very less. Approximately the critical angle of the diamond is 24.4 degrees. So when this 24.4 degrees crosses, means more than the 24.4 degrees, the total internal reflection takes place very much. Due to that total internal reflection, the diamond glitters. For example, look at here, in the diamond, the total internal reflection takes place, diamond glitters. When the light passes through the diamond, so the number of the times the total internal reflection takes place, due to that the diamond appears glitters, or The diamond appears, glitters or brilliance. Another application of the total internal reflection. We know well about the mirages. So actually mirages are optical illusions. It appears as a water body or water collected at a place on the road in the time of summer season on the road. Look at here in this picture, there is a water. Actually that is not water, it is one kind of optical illusion. When we approaches to that water body, actually there is no water present here. So that means it is one kind of optical illusion. This happens due to the involvement of two phenomena. The first one is refraction of the light and the second one is total internal reflection. In the summer season, the air above the surface of the road is very hot than to the higher altitude. In the higher altitude, the temperature is less compared with the surface of the road. In this, the light travels slowly compared with the down. When the light fallen on any object or from the sky, the total internal reflection takes place. Due to the total internal reflection, the image of the tree or object, even sometimes sky, appears on the surface in a virtual manner. So this is one kind of virtual image. Actually, that image appears as to our eyes as a water there or image of the tree at the surface of the road. This is due to the total internal reflection. Means when the light fallen on the object, so the light goes and come back and total internal reflection takes place, then the object appears as a collected at a place. Next, optic fibers. Optic fibers also works by depending upon the phenomena total internal reflection. So actually optic fibers are a small strand like structures. They are very thin, almost 10 to the power of minus 6 micrometers. So these optic fibers are made up of with a glass or plastic, very thin wires. The bunch of the wires form a optic fiber, big optic pipe. Signals, light or pass through this optic fiber. Nowadays, this optic fiber is very useful. This used in the surgeries like a laparoscopy, endoscopy. Doctors introduce that pipes into the body because all parts are not visible to our eyes, the internal parts. So to observe that internal parts on the screen, this optical fiber is very useful. This makes the surgeries very easy. Now nowadays optical fiber also used to pass signals very quickly, like your television signals, some voice signals, some images through this optical fiber. So this optical fiber worked on the principle of total internal reflection. For example, look at here. These are the strands of the optical fibers. This pass light, even it is folded, how it pass light? Actually light travels in the straight manner because of the total and internal reflection. There is the number of the reflections that takes place in the optical fiber. It is about the applications of total internal reflection.